We're going to continue with some of our applications of quadratic equations. Next problem is microbiologists discovered that the number of microbes in a refrigerated food is given by the equation n equals 20t squared minus 45t plus 240, where n is the number of bacteria and t is the temperature in Celsius. Notice it is in Celsius. At what temperature will the number of bacteria be minimal? So if we look at this problem, again, if we start with our x and our y, the t squared corresponds to the x, so we'll write down temperature, and if you want, degrees Celsius, and the y corresponds to the number of bacteria. So here we are just interested in what temperature will the bacteria be in minimal. So if we look at the graph, we're going to be looking for that number. So depending on how it sits. So when we're looking at minimal, again, I want you to associate that with vertex. So the t, capital T in this instance, is minus b over 2a. And the b is a negative 45. So you do want to be careful. We have the first negative as part of the formula. The second negative is part of the actual problem. And then 2 times a, which is 20. And if you divide this out, you get 1.125 degrees Celsius. Now we know that the top is going to be positive, so I want to show you something on your calculator. If you were to do this on your calculator, you want to take the 45 and you want to divide it by 2 and then divide it by 20. And yes, this is really 45 divided by 40, but you may not always have these easy numbers to work with. So you don't want to take 45 divided by 2 times 20, because we're dividing the 45 by 2 and we're dividing the 45 by 20. The problem doesn't ask for it, but the number of bacteria, we plug that temperature back in, is going to give us 214.6875, and this just goes on forever. So you can write this as being 214, or you could write 215 if you wanted to, because we're not counting a bacteria until it actually is totally formed. So a partial bacteria doesn't count. All right, the next problem is going to be kind of a geometric problem. This can be useful if you want to fence off an area. You have a 250-foot roll of fencing in a large field. You want to construct a rectangular area for your garden. What are the dimensions of the largest such garden, and what is the largest area? So we have some keywords here, largest. So if we look at a rectangular area, we have the length and we have the width. And we actually have two formulas that we can actually use before we even get into using the quadratic equations or the quadratic equations. So we have 350 roll of fencing, so that reminds me of perimeter, and the largest area obviously would be the length times the width. So if we look at perimeter is 2 times the width plus the length. you could multiply that through, and you've seen equations that actually have perimeter equals 2W plus 2L, but I think you're going to find it easier to separate that. So all we need to do is substitute what we know. So in this instance, we know the perimeter is going to be 350 equals 2 times W plus L. And the reason I left that 2 out is it will save us if we divide both sides. So we have W plus L equals 175. Now that's really not telling us much, because if we go back to our area equation, we have two dimensions, the length and the width. And if we look over here, we also have the length and the width. So what we can do is rewrite this perimeter equation for width. Now I'm doing the width. You could do the length if you wanted. And then we're going to take this 175 minus L, and we're going to substitute it in the area equation. So area equals length times 175 minus length. And then if we distribute this L, we have area equals minus L squared plus 175 L. Now we're going to go back to what is the largest area, and then we can work from there. So in this instance, we will recognize that this is in the form of ax squared plus bx. So since we're looking for largest area, we can use the vertex formula. So L will equal minus b over 2a, and then the minus b is minus 175 is b, all over 2 times a negative 1, and that gives us the length of the widest area, largest area of 87.5 feet. Now we want to find the width, so we can go back to our first equation, 175 minus 87.5 feet, and that'll give us a width of 87.5 feet. So the optimal area, the largest area, will be 87.5 feet by 87.5 feet, which is a square. And then the area is just the length, or one of the sides, squared. So that'll be 87.5 squared. So the area will be 7,656.25 square feet. Okay, the last problem. The suspension cable between the two towers of the Mackinac Bridge form a parabola that can be modeled by the following equation, where x and y are measured in feet. How far above the water is the cable at its lowest point? Now, one thing I want you to recognize, I'm going to choose a different color here, is that we have our x and y axis, and you'll notice that 0 is the water level of tower, let's call this tower A. You can, when you create quadratic equations, you can, and you're modeling them from real life objects, you can put your origin anywhere you want. So in this instance, they put the origin at the water level. So what we want to know is, what is this height? So if we look at the cable that is connected between these two towers, the lowest point, we want to find how far above the water that is, and you'll see that there is a distance there. So when we look for lowest point, we're looking for this value right here, and that will tell us how far from the water level we are for us to calculate. So we know that the x corresponds to the horizontal distance from the water line of tower A, and the y corresponds to the height of the cable. So at any point on this cable, we can calculate how far from the water line that cable is. So this point is, in essence, the closest to the water. So we're going to use minus b over 2a, and that's going to give us x. So I'm just going to plug the values in. You want to be very careful with your negatives and your decimals. And you'll notice that when I wrote the equation, I separated the 3 digits by a space. That just makes it a little easier to recognize. And if we do this calculation, I'm just going to round it to the nearest foot. That's 1,907 feet. Now, you'll notice that when I use set up the vertex formula, that I identified that we were looking for the x. So this 1,907 feet is the distance from Tower A, which we just arbitrarily called. Well, what we want to know is the height. So we plug that back in. We were actually looking for y, I'm sorry, not the height. Well, it is the height. And if you plug that back in, you get 197 feet. And that is the distance from the water. And that would be our answer. So these problems require that you interpret the variables and then find what you're looking for.